Hi everyone, I'm Shafi Goldwasser, and I'm really honored to speak here. And I will be a very dry scientist after such a moving morning, but this is who I am. And I was lucky to meet Roger really on our calls of the project CETI. And I must say that it's amazing that I kept on trying to remember, did I meet him in person? Because his personality was so looming that even though I think we did only meet on Zoom, I remember that I was extremely flattered where he seemed to say to me, wow, you're doing such good work. But I said, but how does he know? But he had some ability to transfer sort of confidence in you, which was kind of blind, I think, in my case. But I was, it's really so much so that did I meet him in person? I don't think so. I think it was all on Zoom. Okay, anyway, I am the theory lead of Project CETI. So it's not that we are expecting the whales to really do mathematics, but rather we are doing mathematics, trying to analyze in principle whether this project can be how successful can it be? Even if we gather all that fabulous data that we're trying to gather, all this fantastic machinery. And I'm totally not alone. There's all other people who are not here. I didn't have the pictures of people who are here, who are part of the theory. So there's people in Berkeley, Gasper and Andre, and people in Italy, actually, and in London, that's Michael Bronstein, and Or Paradise is my student, and just wanted to make sure that they're present here. And so I still think it's a very good question, is why with theory? I always think it's kind of a little funny, even in that New Yorker piece where they say that there are cryptographers on this project. I mean, it's not like the whales are encoding secret messages, but although you could think of it this way, that the cryptographers have some ability to decrypt very difficult messages. But really, more than that, forgetting about cryptography, I guess what we know how to do and what we give to this project is, first of all, we are very much versed in formulating notions, sort of abstract notions. You know, like, what is it that we're trying to do here? Are we trying to detect, predict, generate, find meaning, translate, then verify our translations? So this is part of what we do, sort of define these things very formally, and then we even can ask questions. Is it really going to be beneficial to playback? You know, is it really going to be beneficial to interact? You know, to achieve this ultimate goal of translation and understanding? Possibly not. Possibly we can do it all just from recording them and analyzing this passively. And then we bring techniques from information theory, linguistics, theory of machine learning, where we really kind of analyze, you know, what would be sufficient condition on the structure of whale communication to enable us to do this translation. It has to be somewhat complex for the whole thing to have a chance to work. And I think Adam, who's my partner in this crime, but he's got a great sense of humor, he always likes to compare the whales to a cow. So he says if there's a happy moo or a sad moo, you know, that would be very difficult to translate to. But we believe that in terms of the whale, we have enough structure to do better. And analyze how much data is needed, you know, then this is all information theoretically, then ask about, are there going to be efficient algorithms to do this even once we collect all that data? Can we do this fast enough? And explore the presence of linguistic cross structures like recursion. So I talk about Daniela, who talks about Roger, who talks about someone else. So we have those kind of constructs in whale language and so forth. In any case, till we get enough data, that's really our vehicle, theory. So this is just a pitch for theory, as I am a theorist. And we've written some papers. The top paper there is with Adam and Or and David Gruber, and then there's another paper from the Italian group and also Shane and Michael Bronstein about social learning across symbolic culture barriers in non-human cultures, and then Gasper has some other paper using linguistic methods. The one thing that's true about all the theory papers, they're not really specific to whales. So we try to generalize, and then possibly it would apply to whale communication. It could apply to other non-human communications, because really what we're trying to do is have like a large framework for unsupervised translation. No Rosetta Stone. It's not like English and French. Not only that there's no Rosetta Stone right in this case, what makes it so difficult is that really the linguistic structure is not going to be the same, and domain is very different, and yet we'd like to do this, right? We'd like to say we have some source, which is the whale codas, we have English, X and Y, and maybe we collect so much data that we could write a language model where we could sort of figure out what is the likelihood of hearing a particular sequence of codas in the source whale language. So suppose we could do that. That seems to be reasonable, given what we know now about language generation, and we're going to collect all this codas and data. We could do that. Still, what's the goal? So what we have done in this work with Adam and Or and David is we say, you know what, let's make a thesis and say, let's assume there exists a translation. It's a mermaid. It's like a function, this F star, and it's a mermaid assumption. So there exists some function that translates. Even that not everybody believes. They maybe use echolocations, is not a word for that. So what we mean by this translation is, I think the example with echolocation, you know, there's something has been said that involves echolocation. So it's not word by word the way you think about translating one language to another, but sort of translation of meaning, okay? And so that's what I mean by the mermaid assumption. And then our goal now, at least we have a mathematical goal, and that is there exists such a thing, we don't have it. But we'd like to be able to come up with something that approximates it. So we'd like to be able to come up with this other function, such that this is sort of mathematical jumbo, that the loss between what the truth is, that thing that exists but we don't know what it is, and the one we find is sort of small. So we expect that, you know, when we get X, which is generated in the whale world, and then we look at our translation versus the real translation, there's sometimes, you know, the loss is not so big. We're trying to minimize that loss. So this is the loss between two of them. And now, I just want to make sure, we do not assume that we know how the whales speak in terms of linguistics, in terms of necessarily what they're talking about, but we do assume something. So for this whole theory to come up, we assume that we have some idea of what's plausible translation and what's not. So for example, just so that, you know, where is the example? Okay, so this is just a picture that says, okay, these are the whales speaking, this is all of English, then there's some sort of translator that is some subset here, okay? And we have we have some probability distribution over the subset, okay? And like what's plausible and what's not plausible, and the example that I will use, this is a slide I stole from Adam, is that it's fairly unlikely that they're talking about whether they got the new smartphone or not, but it might be more likely that they're talking about the fact that a baby whale was born, if we think about the recent event, okay? So if we had a distribution that would tell me this is unlikely, this is likely, then this is our assumption, we're gonna use that in order to find that function that approximates the truth, okay? And now we're sort of in the realm of mathematics, and we can write this formulas up there where there's this loss function, so we're given F, which is the one that we're attempting to figure out whether that's the right translation. We're giving we get some distribution over what the whales are speaking about, and then we have this rho, which is this magical prior that tells me likely, not likely. That's the loss function. Now we're trying to find an F that would sort of minimize this loss. And it actually leads to an algorithm. So we say, here's an algorithm. So you guys all should say, well, if you have an algorithm, why aren't you using it? Well, there are two reasons. First of all, we don't have this enough data. This algorithm needs actually data. Second of all, we don't have this prior, but that we will talk about in a minute. But third of all, this algorithm is not efficient. So in other words, we have this notion of an information theoretic algorithm, which says in principle, if you collect enough data and you had all the time in the universe, you could do it. Now the question is to get a fast algorithm. But you know, machine learning has proven to us that even though in principle what they're doing is impossible, even mathematically, they manage to do all kinds of optimization and approximations and succeed. So really the interesting question is, what is this assumption that I have a prior that maybe they are talking about the smartphones? Who am I to say they're not? How, well, you know, I guess you as scientists know that there's something that you do know from observation, okay? And you could think of this prior coming from existing even large language models or GPT-X, whatever. That is what it might be likely given what we've observed. All right, that's really kind of all I'm going to say. So at the end, we're going to have this unfishy algorithm, which gets samples from the distribution, gets a prior, and knows sort of like what the function is supposed to look like, or sort of assumes, and comes up with it. Comes up with this translator. It's not currently efficient, but we never know. That's my take. That's it. That's my last slide. So we have a setting. We have a goal that we're trying to minimize the error with respect to this alleged mermaid function. And then we have some toy models where we actually analyze how much data you would need to make that unfishy thing work. And for the toy models, it's not actually much more expensive than when you have a Rosetta Stone. So the fact that it's unsupervised does not kill us. And second of all, this is kind of interesting that the error in our translation is really, or the error would be 1 over, so inversely proportional to how complex the language is. In other words, the more complex it is, the better situation we are. The more structure there is, the better situation we are, and also to the common ground. So the closer it is to us, the closer it is that they're talking to things that the target language is talking about, English, then also our error will go down. So the next steps are like, faster algorithm, weaker assumption than just knowing this prior, more models to analyze. Thank you.